The purpose of this video episode is to take a look at the connection between that we have of delta G, or Gibbs free energy, and equilibrium. Now, recapping delta G, we know that delta G, if that comes out negative for the conditions and for as the reaction is written, the reaction is spontaneous. Whereas if we get a value of positive for delta G, that's an indication that for the reaction as written and under its conditions, the reaction would be non-spontaneous. And looking at our reaction, here we have our A plus B gives us C plus D. Let's say we calculate, we get a delta G of negative. That negative delta G indicates that this reaction is spontaneous in the forward direction as we move from left to right and proceed from reactant to product. What this also indicates is that we'd have a delta G that would be positive if we flip the reaction, or it's a positive value for the reaction in the reverse direction. So if the reaction is spontaneous in the forward direction, that means it's going to be non-spontaneous in the reverse direction under the same conditions. Now, if we recall, in an equilibrium reaction, the reaction occurs in both the forward and the reverse directions. Now let's remind ourselves what it means to be at equilibrium. Specifically, when a reaction is at equilibrium, the rate in the forward direction is equal to the rate in the reverse direction. Because the rate in the forward and reverse directions are equal, the concentrations of reactants and products are remaining unchanging. Visually, it would appear as if nothing is occurring. Now, our key concept here is because the rate is equal in the forward direction to the reverse direction, at equilibrium, under these circumstances, delta G specifically is equal to 0, in that the reaction is occurring at an identical rate in both the forward and reverse directions when at equilibrium. Now, if we recall, with equilibrium reactions, they can do things to try to reach equilibrium, such as when a reaction shifts right, that's an indication the reaction is not at equilibrium, and the reaction is making an attempt to reach equilibrium by shifting to the right. In an equilibrium system, when a reaction is shifting right to try to reach equilibrium, that's indicative that the delta G right now is negative, indicating the reaction is spontaneous in the forward direction. On the flip side, if we say that a reaction is shifting left in its attempt to reach equilibrium, that's indicative that the reaction delta G indicating it's negative or spontaneous for the reverse direction as the reaction tries to reach equilibrium. However, once all shifting is done and the reaction actually reaches a state of equilibrium, this is an indication under these conditions that the delta G would be equal to 0 for the reaction under those conditions. Now, that delta G is equal to 0 at equilibrium has several implications for equilibrium type of problems. Let's run through an example. In our example problem, we have what's going to be a saturated solution. Now recall, if there's not enough ions in solution, the reaction would get driven to the right. Some of the solid would dissolve, bringing the ion concentrations up to equilibrium concentrations. However, if the ion concentrations are too big, the reaction is going to shift to the left, and we'd see solid precipitate forming as the ion concentrations are lowered in an attempt to reach equilibrium for our saturated system. Now, what we're asked to do here is determine, is the reaction spontaneous in the forward direction, spontaneous in reverse direction, or is the reaction at equilibrium, specifically under standard conditions? Now, when we indicate standard conditions, that's denoted by this little degree sign. Now, when we say standard conditions, in this case, these are both aqueous ions. 1 molar concentration is standard conditions. If something were gaseous, 1 atmosphere pressure would represent what we refer to as standard conditions. We can calculate our standard enthalpy of change for this reaction by going through the standard practice of products minus reactants. Our standard enthalpy, change in enthalpy for the reaction is a positive 65.5 kilojoules. We can do likewise for the change in entropy of the reaction, doing products minus reactants. Our change in entropy for the reaction is a positive 0.0029 kilojoules per Kelvin mole. Our standard condition temperatures are 25 degrees Celsius, which converts into 298 Kelvin. We can now calculate our standard delta G to answer our question for the problem. We have our delta H, or change in enthalpy for the reaction, we have our temperature, and we have our change in entropy. Solving for delta G, we get under standard conditions our delta G is a positive 64.64 kilojoules. Now what this tells us is that under standard conditions, when the concentrations of the aqueous ions are 1 molar, this reaction is non-spontaneous in the forward direction. However, the positive delta G for the forward reaction means we have a negative delta G for the reverse reaction. Now what that tells us then is the reaction is spontaneous in the reverse direction under standard conditions. The implications of this is that when these aqueous ions have concentrations of 1 molar each for standard conditions, those concentrations are too big. Because those concentrations are too big, the reaction shifts left, converting some of the ions into solid precipitate. When we say it shifts left, that's another way of saying the reaction is spontaneous in the reverse direction. Our delta G before indicated with a positive number, it was non-spontaneous in the forward direction, so that means in the reverse direction, or shifting left, the reaction would be spontaneous. Let's change our problem now to see if the reaction spontaneous or non-spontaneous, forward and reverse directions are at equilibrium when we have conditions that are something other than standard conditions. In this case, when the silver is 1 times 10 to the minus 6 molar, and the chloride is also 1 times 10 to the minus 6 molar. We have a new equation with delta G that ties together delta G with our reaction quotient Q. This delta G that we have is non-standard conditions because we lack the little degree symbol here that indicates standard conditions. Our other delta G here is for standard conditions because we have our degree symbol indicating standard conditions. Going back to our equilibrium material, Q represents something known as our reaction quotient, a ratio of reactant to product when conditions are other than at equilibrium. Take a quick review now. Our equilibrium constant, KSP, it's an SP because we have a saturated system of a solid in equilibrium with its aqueous ions, is products over reactants. Our products would just be the silver concentration times the chloride concentration. Our reactants, because they're in the solid state, drop out of our equilibrium expression. Our setup for the reaction quotient Q is the same. It's the same as what we have for our equilibrium constant. Do a quick review of Q and K. If we calculate a reaction quotient that's bigger than K, that means we have too much product, and the reaction would shift to the left to try to alleviate too much product and drive the system to reach equilibrium. On the other hand, if our Q value comes out less than our equilibrium constant, that tells us we have too much reactant, or another way to look at too little product, the reaction will shift to the right in an attempt to reach equilibrium. And then continuing our review, when Q is equal to K, that's an indication that the system is at equilibrium and there's no need to shift in either the forward or reverse directions. Setting up our equation, we already have our delta G for standard conditions figured earlier of positive 64.64. Our R value is 0.00831 because our unit we have to use is kilojoules to be consistent with our kilojoules of our delta G. Temperature is 298 Kelvin, and our Q expression is the silver concentration times the chloride concentration. Placing in our concentrations of silver and chloride that we were given of 1 times 10 to the minus 6 molar, we can now calculate our delta G for our non-standard conditions. Calculating, we get a value of our delta G for these particular non-standard conditions of negative 3.78 kilojoules. Now what this tells us is this particular reaction under these conditions is spontaneous in the forward direction. For equilibrium, that's another way of saying that under these conditions the reaction is going to shift right to try to reach equilibrium. It's an indication that the ion concentrations of silver and chloride are too small. We're below the saturation point, so some of the solid is going to dissolve. The reaction is going to shift right, bringing the ion concentrations up until the system reaches its saturation point at equilibrium. Another type of calculation is we can use delta G to calculate a value for the equilibrium constant for equilibrium reactions. Here's the equation that we just used, but we'll switch it up a little bit. When we're at equilibrium, delta G is going to be 0. And when we're at equilibrium, Q is no longer Q, but it's referred to as K, the equilibrium constant. Using our standard conditions delta G value that we found earlier, positive 64.64 kilojoules, and our value for R, 0.00831, our temperature is still 298 Kelvin. The only unknown we have is the equilibrium constant K. Delta G for non-standard conditions is 0 because this will be equal to 0 when the system is at equilibrium. When we're at equilibrium, we'll be able to solve for the equilibrium constant K. Rearranging, we get negative 64.64 divided by 0.00831 times 298 is equal to our natural log of our equilibrium constant K. To solve for K, we take the anti-natural log of negative 26.10, and that'll give us our equilibrium constant. Solving for K, our KSP, we get 4.6 times 10 to the negative 12th. Another thing we can use the connection between delta G and equilibrium for is phase changes. Things such as boiling points and melting points. When those are occurring, the system is at equilibrium. If we go back and remember our phase diagrams, here we have one atmosphere. This point, solid to liquid, would be our melting point. The liquid to gas boundary would be our boiling point. The phase change occurs, in this case solid to liquid. That's an equilibrium between solid and liquid. And over here it's similar, an equilibrium between liquid and gas when we fall right on the boundary between the phases. Another aspect is that when conditions are one atmosphere is considered standard conditions, and these specific melting and boiling points would be what we refer to as our normal melting or boiling points. The implications of this are when we're looking for a normal boiling point or melting point, because we're at one atmosphere pressure, that's considered standard conditions. And also a boiling point or a melting point, we're at equilibrium. So what we can do is, under standard conditions, make this delta G equal to 0. We can solve for our temperature, and that would give us our melting or boiling point, our normal melting or boiling point. This would be an example problem where we're going to determine the normal boiling point for our compound ethanol, C2H5OH. Boiling point would be the equilibrium phase change between the liquid and the gaseous phases. We'll set our delta G value equal to 0 because it's going to be at equilibrium for this phase change. We can calculate our delta H using products minus reactants. We get a positive 41.7 kilojoules. Likewise, we can find our delta S, or entropy of a reaction, also doing products minus reactants. We get a positive 0.1223 kilojoules per Kelvin mole. We can now solve for T, which will give us our normal boiling point for the liquid turning to gas equilibrium of ethanol. Solving for T, we get 341 Kelvin, or 68 degrees Celsius, and that would be our boiling point for ethanol, or the equilibrium phase change for liquid to gas.